Dear students, welcome back to my YouTube channel. We were discussing about the topic molecular rearrangement and transformation, and in this lecture I would like to discuss with you Baeyer Villiger rearrangement. Baeyer Villiger rearrangement, it is named after Adolf von Baeyer and Victor Villiger, and it is a rearrangement reaction take place to an electron deficient oxygen, and it happens oxygen insertion. And Baeyer Villiger reaction, it is an acid catalyzed conversion of ketone into ester. You are studying with ketone here, and it converted into ester. And cyclic ketone, it converted into lactone in presence of peroxy acids. Peroxy acids used are peroxyacetic acid, peroxybenzoic acid, monoperoxyphthalic acid, trifluoroperoxyacetic acid, and metachloropperoxybenzoic acid. This is the structure of metachloropperoxybenzoic acid. And here you have an oxygen here, and this oxygen you can insert in between two carbon. So in the case of ketone, you can insert oxygen here in between these two carbon, and cyclic ketone you can insert one oxygen in between these two carbon by using peroxy acids. And coming to the mechanism of the reaction, you are starting with ketone, and in the presence of acid, this lone pair oxygen get protonated first, that is this one, and you can see that this oxygen contain lone pair, and this get protonated, and you get a protonated ketone, and this become more electrophilic, and this peroxy acid oxygen, one of its oxygen, it is contains lone pair, and it's highly nucleophilic, and this nucleophilic oxygen attack this carbonyl carbon, that is electrophilic center, and you get an intermediate like this. And this intermediate, this oxygen bond is very weak, and this break very easily by the expulsion of a very important leaving group, and RCOO minus is a very good leaving group, and at the same time a rearrangement take place, that is an alkyl migration take place, and this alkyl R group migrated to the electron deficient oxygen, and you get this product like this, and this is finally deprotonated. This proton get removed, and you get an ester. This is our final product. So you're converting a ketone into ester. So it's a very important reaction. Normally you cannot convert a ketone by using ordinary oxidizing agent like KMNO4. And here you can see that in this oxygen there is an 18. This is isotope labeled oxygen. The reason for labeling this isotope with this oxygen is to understand whether the product contains the same oxygen. That can be monitored, whether this oxygen, this oxygen is from here or from peroxy acid. That can be understood by isotope labeling experiment. And in the case of peroxy acid, the best peroxy acid is CF3CO2H, because CO3H, because trifluoroperoxy acid, peroxyacetic acid, because CF3CO2, that is a very good leaving group because it can stabilize this anion. Okay, in the case of cyclic ketone mechanism, this is the reaction. This is cyclohexanone. In the presence of peroxy acid, you get the ring expanded product, and oxygen is get inserted in between these two carbon. And how about the mechanism? In this particular case, this is the electrophilic carbonyl group, and this peroxy acid oxygen is nucleophilic, and this attack this carbonyl center and double bond break, and you get an intermediate like this. This is the intermediate, and in this intermediate a rearrangement take place. First this O bond, that's O single bond, is very weak and carboxylate leave, and alkyl migration take place. This alkyl group get migrated to this oxygen. At the same time lone pair on this oxygen stabilize this positive charge, the carbocation that formed here after the migration, and it stabilizes the cation, and you get a product like this, right? You can see that this is the product. Then finally the H plus get removed, you get final product, that is cyclic lactone, right? Okay, and more examples for Baeyer Villiger reaction. In the case of unsymmetrical ketone, what happens? So you have seen in previous two examples symmetrical ketones, and if you have unsymmetrical ketone, that is a methyl group in one side and tertiary butyl group in another side of carbonyl bond. So here the question is whether the oxygen get inserted in between this methyl and carbonyl, or in between tertiary butyl and carbonyl. It is an oxy-insertion reaction, of course, but we have seen that the oxygen get inserted in between carbonyl and tertiary butyl carbon and the CC bond. Here, the group get migrated normally, a group which is having ability to supply more electron, that is more tonating capacity, tonating electron. A group which can tonate more electron will migrate. So among alkyl, ease of migration is like this: tertiary having more electron tonating capacity than secondary, than primary, than methyl. So tertiary butyl will migrate. And if you have a methyl group and or an alkyl group and an aryl group at the carbonyl in the presence of acid, where does this oxygen get inserted? That means which group will migrate, whether alkyl or aryl. So we have seen that the aryl group get migrated and oxygen get inserted here, and aryl having more preference than alkyl. Among aryl, the ease of migration is like this, and if you have a substituent at alkyl aryl group, we have seen that the para-methoxyphenyl, that is the methoxy group at para position of phenyl, and para-toluene, that means CH3. So this is having more migratory aptitude because it contains electron donating group, and this toluene having more electron migratory aptitude than phenyl, but para-chlorophenyl having less migratory aptitude. That means the chlorine is electron withdrawing, and that is why it has less ability to donate electron. And this reaction summarizes the migratory aptitude of alkyl and aryl. And in this particular example, if you have an R here, that is alkyl group, and R is varying like a methyl, ethyl, isopropyl, and tertiary butyl. And in the presence of peroxy acid, you get a ratio of two products. And in first case, oxygen is get inserted in between aryl and carbonyl, that is phenyl group is migrated. And in second case, the alkyl group is migrated, and you have seen that we can see that the ratio of product is changing when you go from methyl to tertiary butyl. So if you have a methyl and phenyl or aryl, you get this product, that is oxygen get inserted in here is less. But when you have a more electron donating group ethyl, you have a 6% the alkyl migration and 87% aryl migration. And when you have a more substituted isopropyl, the ratio of the aryl migration is decreased and alkyl migration is increasing. And if you have a tertiary butyl, that is more electron donating capacity, the aryl migratory aptitude is less, than alkyl migratory aptitude is higher. So you can see that among alkyl and aryl, the ease of migration is tertiary butyl is having more donating capacity than substituted alkyl, than phenyl, than ethyl and methyl. That means the group able to stabilize the positive charge is having more migratory aptitude. And another example, you can see that in this particular example, phenyl and an electron donating group are here. So in the presence of MCPBA, and this group, the left one, having more electron donating capacity than phenyl, thus get migrated and oxygen get inserted here. But if you have a tertiary butyl here, you can see that tertiary butyl is migrated and oxygen get inserted here. So the same case, tertiary butyl is having more migratory aptitude. It is understood from this example also. And three more examples. In this cyclic compound, Baeyer Villiger oxidation, the oxygen get inserted here. Why it is inserted here? Because this is this is tertiary carbon atom and this is secondary carbon atom, and tertiary having more migratory aptitude than secondary one. And second, this example, it is having a phenyl group here and a nitrophenyl group here. In the presence of peroxy acid, you can see that the phenyl is having more migratory aptitude, because here it contains nitro group, it is electron withdrawing group. And example 7, you can see that this bicyclic system, and the oxygen is get inserted here. The reason is this is tertiary alkyl group. This is only secondary alkyl group, and this having less migratory aptitude, and oxygen get inserted here. And one more example, you have an carbonyl here, and the oxygen get inserted here, and you can see that this MCPBA peroxy acid doesn't react with this alkene, and it only get inserted here in this particular system, and oxygen get inserted here, not in this carbon atom, because this is a tertiary and this is secondary. And another example, 1,2-diketone, in the presence of peroxy acid, it gives anhydride. For example, this is 1,2-diketone. In the presence of acid, oxygen get inserted here and will form anhydride. And in summary, Baeyer Villiger reaction, it is a rearrangement to electron deficient oxygen or oxy-insertion reaction, and it is an acid catalyzed conversion of ketone into ester and cyclic ketone into lactone in the presence of peroxy acid, and in some cases diketone converted into anhydride. And trifluoroperoxy acid and MCPBA are the best reagent and commonly used. And the migratory aptitude is like this. Usually the group migrate which is able to apply supply more electron. And among alkyl, the ease of migration is like this. Tertiary is having more migratory aptitude than secondary, which is having more than primary than methyl. Among aryl, ease of migration is paramethoxyphenyl is having more migratory aptitude than toluene, than phenyl and parachlorophenyl. And when you have an aryl and alkyl group, aryl migrate in preference to alkyl. But in the case of tertiary, we have already seen it is having more donating capacity than aryl phenyl group. Okay, thank you for watching.